Hello, differential equations class. It is very strange to be talking to you through a camera, but I hope you had a good spring break, and I really hope the rest of the semester goes well. I really do want to work with you to make this work this semester. It's a tough situation, but hopefully we can make it work. So, hence the videos. Okay, so we're looking today at section 3.4. Before the break, we were looking at linear systems of the type y prime equals a times y, where, a times y, where a was a real valued matrix. So a nice example of this is y prime equals, got to look at my notes, 0, 5, negative 2, negative 2, 0, 5, negative 2, negative 2 times y. So this is my a right here. And just to remind you, we had determined that if we could find eigenvalues and corresponding eigenvectors for this matrix, we could build solutions out of them. And if we were lucky enough to find two independent solutions that way, then we got all solutions as an arbitrary linear combination of them. Okay. So that's fantastic. So remember, that has us looking for solutions to AV equals lambda v, but where v is not 0. My eigenvector has to be non-zero. So if you remember, we said that means a times v minus lambda v has to equal 0. We're tempted to factor out the v, but as is, that's a matrix and that's a number, so that doesn't work so well. But I can introduce the identity matrix, and multiplying by the identity matrix doesn't change anything. So now, instead of just multiplying by the scalar lambda, I'm multiplying by the identity matrix, scaled by lambda. So I'm multiplying by a matrix, and I can factor it out. So a minus lambda I times v would equal 0. And then we got from that that since v could not be the 0 vector, that meant that a minus lambda I, the determinant of a minus lambda I had to equal 0. And that's 0 the number, not 0 the vector. All of these were 0 the vector. Okay. So that was good. The solutions to this equation would give us our eigenvalues. So let's try that here. Okay. If I look at a minus lambda I here, I'm just subtracting lambda from the main diagonal. So I'm going to get negative lambda, 5, negative 2 minus lambda. So if I calculate the determinant of a minus lambda I, that's just going to be this diagonal product, negative lambda times negative 2 minus lambda, minus a negative 10, so plus 10. So let's see, if I distribute that out, this is going to give me a lambda squared plus 2 lambda plus 10. Okay. So that's what we call the characteristic polynomial, the determinant of a minus lambda I. The characteristic equation is what I get when I set that equal to 0. Now notice that's always going to be a quadratic equation in lambda, and it's always going to have real coefficients if I started with a matrix that has real coefficients. Okay. But usually I try to factor, it doesn't look like it's going to factor, so I'm going to use the quadratic formula here. So I'm going to get lambda is the opposite of 2 plus or minus the square root of 2 squared will be 4. Minus 4 times 1 times 10, so minus 40, all over 2. So that's negative 2 plus or minus the square root of negative 36 over 2. Now, if I wanted to just work in the real numbers, I would have to stop here, because I can't, in the real numbers, take the square root of a negative 36. But if I give up on that, that means I don't have any eigenvalues. If I require that they be real, I'm not going to have any here. And I kind of liked having eigenvalues. So we're actually going to go ahead and work in the complex number system. So in the complex number system, we define I to be the principal square root of negative 1, which means that I squared is equal to negative 1. So I is like a number that's sort of half positive and half negative. So when you combine two of them, you get a negative number. Okay. So with that, I can rewrite this. I can say this is negative 2 plus or minus The fact that it's negative means it's going to be a multiple of I, but then I just take root 36, so I get 6I all over 2. I can factor out a 2, so I get 2 times negative 1 plus or minus 3I all over 2. Cancel those 2's. My lambdas are negative 1 plus or minus 3I. So if I allow myself to work in the complex numbers, I get some eigenvalues. And that's what I want, because that's going to help me to build some solutions. Okay, so we're going to just expand and work, even though we're ultimately trying to find real solutions to this real system of differential equations, we're going to allow ourselves to pass into the complex numbers when we find our eigenvalues and ultimately our eigenvectors. Okay. One thing I'll point out is that if you have a quadratic equation with real coefficients, and you always will if you got it as the characteristic equation for a real valued matrix, then if you have complex roots, they'll always come like this in what we call conjugate pairs, where that number is the same, the I part can be either plus or minus. So let's review just a little bit about complex numbers. A little of this will be review, and a little of this might be something that's new as well. Okay. So when I write a complex number, the standard form for it is going to be A plus BI, where A and B are real numbers. So I've got a real number and then plus a multiple of I. Of course, if B is 0, then I don't have an imaginary number part at all, and I just have a real number. If A is 0, we would say I have a purely imaginary number. If A and B are both non-zero, I have a complex number. So the complex numbers are everything I can build using the real numbers and this new number I. Okay. We say here that A is the real part. And let me get a new marker. And we say that B is the imaginary part. Now, one thing that's super important here, the imaginary part is a real number. The imaginary part isn't BI, it's just the coefficient in front of the I. Okay? That's how we define that. Okay, so hopefully that's review, and as we start working examples where we've got complex eigenvalues and eigenvectors, we'll review some of the algebra for working with the complex numbers. But something that some of you may or may not have seen before is Euler's formula, which is that e to the it is cis of t, and that stands for cosine of t plus I times sine of t. So this formula here gives me a connection between exponential functions, which we've seen are incredibly important in differential equations, and sine and cosine function, which it's going to turn out are also incredibly important in differential equations. And you might sort of look at that and say, why? And who gets to decide that? Okay. Well, what I'm going to do is just illustrate a reason why this rule, why this formula actually does make sense. Okay. So let's just say I was multiplying e to the I times t1, and I wanted to multiply that by e to the I times t2. Okay. So I know that if I'm multiplying two things that have the same base, I can just add the exponents. So using the rules of exponents, this should be e to the I times t1 plus I times t2, and I can factor out the I. So that's e to the I times t1 plus t2. That's just using some rules of exponents. But now let's apply Euler's formula to each side. If I looked at this, this should be cosine of t1 plus I times sine of t1. And I'm multiplying it by this, which would be cosine of t2 plus I times sine of t2. if this works, it's supposed to be the same as this. Now, I'm not doing a proof here. I'm doing an illustration. If I were proving this, I would work with one side at a time. I have told you this is true. I'm just illustrating it by simplifying both sides. So here, this should be cosine of t1 plus t2 plus I times sine of t1 plus t2. So, let's work this out. If I were going to multiply this out, I just FOIL this out. So I would get cosine of t1 times cosine of t2 plus I times cosine of t1 times sine of t2 plus, inside terms, I'm going to get I times sine of t1 times cosine of t2 plus my last terms, I'm going to get an I squared times sine of t1 times sine of t2. Oh my goodness, that took up some space. Okay. Let's sort of consolidate. Now notice there's an I squared here. Remember, that's just a -1. So this term is actually part of the real part of things. So I'm just going to say this is cosine of t1 times cosine of t2 minus sine of t1 times sine of t2. Those are the two real terms. And then this term and this term both have an I in them. So I'm just going to factor out that I. The imaginary part, which is the real coefficient of the I, is cosine of t1 sine of t2 plus sine of t1 cosine of t2. Now if we look at what we had on the right-hand side, the real part was cosine of t1 plus t2. Now, if you remember your sum formula for cosine, you can work out what that is. If you don't remember your sum formula for cosine, you can cheat and look over here and see that the sum formula for cosine, cosine of t1 plus t2, is cosine of t1 times cosine of t2 minus sine of t1 times sine of t2. That is cosine of t1 plus t2. Now if I look at the imaginary part, that's sine of t1 plus t2. So let's see, if I remember the sum formula for sine, I could work that out. If I don't remember the sum formula for sine, I can cheat, and I can see that it's cosine of t1 times sine of t2 plus sine of t1 times cosine of t2. Okay. So those sum formulas, which you could look up if you don't remember, but that's exactly what they are. I'll write them out for you real quick. Cosine of a plus b is cosine a cosine b minus sine a sine b, and sine of a plus b is sine a cosine b plus cosine a sine b. So this was just applying those formulas with t1 and t2 instead of a and b. Okay. Again, not a proof, but just an illustration of why it makes sense to have this connection between seemingly unrelated things, which is the trig functions and the exponential functions. Okay, I'm going to end this video. We're going to resume with the next video. We'll come back with that same matrix and start trying to find the eigenvectors that go with our eigenvalues that we found and see if we can build some complex solutions. And then our goal is ultimately to find the real solutions. So we're going to have to figure out how to go from the complex ones to the real ones. And we will.